This is a makeup lecture for Stat 401B, Fall Semester 2015 at Iowa State University. The discussion here is going to cover Section 6.2 of James Whitten, Hastie, and Tibgerani's book. I'll discuss so-called lasso regression, ridge regression, and elastic net regression. These are alternatives to ordinary least squares that is used in standard multiple linear regression analyses, particularly appropriate where one has a large number of predictors, where P, the number of predictors, is large. Having a large number of predictors is in one sense a good thing because that hopefully provides adequate modeling flexibility when one goes to describe Y in terms of the inputs. But once one has a large number of predictors and large flexibility of the form that one is fitting, one is then faced with the problem that in P dimensions, in data cases, that is, in particular instances, cap in instances of x1, x2, up through xp and y, are of necessity sparse. One doesn't have a lot of data, and that puts one in the position of being in danger, in fact almost certainly facing overfitting if one makes use of ordinary least squares, that is standard multiple linear regression based on a standard form that says y is beta naught plus beta 1 x1 up through beta p xp. Now, one thing that one might try to do or think about doing in this context is say, well, I'll look around and not use all p predictors, but I'll pick some smaller number of them. If I have 1,000 predictors, I'll look around and see if I can't find 10 or 12 of them that do a good job of describing Y. And what that leads one to is the notion of looking at all possible reduced models from a full model. That is, thinking about quote-unquote all subsets regression. For large P, that's impractical. It's impossible. It's a combinatory problem. There are 2 to the P minus 1 different sets of predictors that one might choose from P. So if P is 100, you're talking about I believe it's something like 1.3 times 10 to the 31st or some such number of models that you just can't search over all those models looking for a small cross-validation error. And so the idea here is to recognize that a reduced model fit zeroes out some coefficients and thereby more or less shrinks y hat values toward y bar. That's true not only in multiple regression, but if you think about what we did in factorial analysis, if you go back and sort of stare at say 2 to the p factorials and think about, well, what do I get for y hat values, predicted values, when I assume that some of the effects are negligible. If I use the reverse Yates algorithm or I add fitted effects for balanced data, what do I get for y hat values for situations where I assume some effects are negligible? Well, what you'll find is that your y hat values look less like the combination means, less like the y-bars, and more like the overall grand average uh, of the y-bars. And that's true uh, in in factorial analyses. It's true in regression analysis that uh, reduced models uh, tend to have y hats that are more like the average y than are y hats for a full regression model fit by multiple linear regression. So what we're going to try to do is to uh, find predictors, uh, find models, maybe I should have said not a set of predictors, but a model indexed by a real number uh, parameter that we can hope to choose in order to make the cross-validation error sum of squares small. So instead of sorting through all possible submodels, what we're going to think about, what we hope to be able to do is to just pick the value of a real parameter that we're going to call lambda and pick that in a way that will make the cross-validation error sum of squares a good one. This enterprise depends, before we begin, on standardizing the inputs x1 through xp. I talked a little bit about that in class before the Thanksgiving break. Uh, that only makes sense if I'm going to think about uh, finding predictions that are based on somewhat smaller uh, regression coefficients. Uh, I don't even know what I mean by small if I'm thinking about coefficients where the x's have units, because if I multiply the uh, uh, units of x by 10, so instead of talking about uh, inches, I'm talking about tens of inches, that means the coefficient of, of the x needs to go down by a factor of 10. And so the notion of the size of a regression coefficient when you haven't standardized the, the inputs really has no meaning. So we're going to first standardize the inputs, and then the so-called lasso problem is this, that one, for a particular choice of a number lambda, seeks to find coefficients that I'll call BJ super lasso. So they're going to be lasso coefficients. To optimize, this is the ordinary, well, it's the error sum of squares for a particular choice, beta naught through beta 1 through beta p, plus this lambda times the sum of the absolute values of the coefficients on x1 through xp. Okay, so this is a penalty on the size of the regression coefficients. We don't penalize beta naught, so it's just beta 1 through beta p that we look at their absolute values. And the idea is if that lambda was really big, then one would want betas that were close to 0, because that would give me a big penalty here, and that would just swamp the size of this error sum of squares term here. And so in order to get a small overall penalized sum of squares, I would want betas, or I would want b's, b lassos that were close to 0. That's the lasso version. There's a so-called ridge version that for a coefficient lambda, again bigger than 0, one chooses coefficients bj that optimize, again, here's your essentially the error sum of squares plus lambda times the sum not of the absolute values of the coefficients, but of the squares of the coefficients. You can imagine that these two are just different ways of saying I'm going to penalize myself for the size of the regression coefficients that I use. There is a compromise between these two ideas, something called an elastic net, that for a value of lambda, I see I've superscripted that, and then I didn't superscript it down here. You'll just have to ignore that. Lambda bigger than 0 and a number alpha between 0 and 1. I choose coefficients, elastic net coefficients, that optimize. This is essential. This is the error sum of squares. I've now written it with a 1 over n in front of it in order to match the GlimNet version of the optimization criterion. GlimNet's the software that we're going to use. It doesn't matter. I could multiply this whole thing through by n, and I just have a different lambda, a lambda that is a factor of n less than the one we're talking about in this formulation. And lambda times a weighted average. So there's an alpha and there's a 1 minus alpha. Here is the sum of the squared coefficients. Here is the sum of the absolute values of the coefficients. And for reasons that aren't clear to you at this point, it's common to put a 2 in there. This is, in some sense, a bridge between lasso and ridge. It's a compromise between lasso and ridge. The motivation here for this formulation is that there are these three optimization problems: lasso problem, ridge problem, and elastic net problem, are unconstrained optimization problems. Those unconstrained optimization problems have corresponding constrained versions that have some intuition behind them, and that's what I'm going to talk about next. For every lambda in one of these problems, lasso, ridge, or elastic net, there is a corresponding number t that I'm going to talk about in a second, and vice versa, so that the same set of coefficients that solve these unconstrained optimization problems will solve the corresponding constrained optimization problems. So what am I talking about? Well, for the lasso, I could phrase a constrained optimization problem that says for t bigger than 0, minimize the error sum of squares subject to this sum of the absolute coefficients being less than or equal to t. The ridge version says for t bigger than 0, minimize SSE subject to this sum of coefficients squared less than t. And then the elastic net version is to minimize the error sum of squares corresponding to this quantity, which is essentially a weighted average of the sum of the squares of the coefficients and the sum of the absolute values of the coefficients being less than or equal to t. If you look in James, Witten, Hastie, and Tibshirani, you will find pictures on page 222 that go with these first two cases, and they are roughly these pictures. So we're thinking here of a p equal to 2 case. That is two predictors. So there's a beta 1 and there's a beta 2, and this thing here is a contour plot for the error sums of squares. Now, the lasso criterion says subject to sum of absolute values of betas being less than or equal to t. Well, that's this grayed in region here. Subject to that, make the error sum of squares as small as possible. So instead of getting to the bottom of this uh, valley, or this depression, and using an ordinary least squares estimate of uh, the betas, I get moved over here to this beta hat lasso. Uh, and what's kind of interesting about that is that by virtue of the fact that this region has sharp corners, uh, that often means that uh, the solution to this optimization problem lies on an axis. And lying on this axis, for example, in this problem, means that beta 2 is 0. So this is a way of phrasing an optimization problem that tends to make some of the betas, some of the b's in a multiple regression be 0. That is, gives me a prediction equation that has not p predictors in it, but less than p predictors in it. That's the case for the lasso. The ridge, the region is, if you think about it for a while, you'll come to the conclusion that it's a circle. And so the idea is, here's the contour plot for the error sum of squares, and I have to stay inside the circle with my optimizer, my constrained optimizer, and get as far down into that depression as I can get. So instead of having an ordinary least squares set of coefficients, I get coefficients there, beta hat ridge. What's interesting about this second cartoon is that you will notice that it's possible uh, that the ordinary least squares coefficients are both positive. We're up in the first quadrant here, but the ridge coefficients, beta 1 is, or B1's positive, but B2 has fallen negative. For what it's worth, the elastic net version of this picture is sort of a compromise between those two pictures. The shaded region still has corners like the lasso, and therefore sometimes gives you the nice property of having absolutely zeroed out coefficients, but at the same time it's kind of more rounded. Even there are sharp corners, but every place else there's not not a not a circular uh, curve, but a something that is rounded. Um, the result of using lasso or elastic net uh, is to sometimes completely zero out some of the coefficients. So this word should be completely. Uh, in thinking about what this stuff does, uh, big lambdas correspond to small t's. Big penalties on these sum of absolute betas or sum of betas squared basically force you to use small absolute betas or beta squared, and that corresponds to small t's. That is, b's near zero. B's near zero produce predictions that are pulled toward y bar. And basically what that means is that the predictions can't chase extreme data points. Since the predictions can't chase extreme data points, you get some control of overfitting. On the other hand, if you have small lambdas, that corresponds to big T, and these methods turn out to be essentially ordinarily squares. That's the thinking about the methods. That's the high level overview of what they intend to accomplish. There's the question of how to implement them. And there's a wonderful R package called glemnet that will allow us to do cross-validation choice of lambdas for lasso, for ridge regression, for elastic net, and to do corresponding prediction and fitting. So what I'm going to do is in this part of the presentation now, I'll make a second video that shows the use of uh, the glemnet analysis on the Ames house price data set that was used in the Stat 401 lab. Uh, you should know that by default, glemnet does the standardization of the predictors that are behind it does it behind the scenes, and it just goes ahead and reports regression results in terms of the original uh, non-standardized predictors. Uh, its default is to not use the lambda exactly optimizing the I've said penalized here. I don't mean penalized. What I really mean is the cross-validation error sum of squares, but rather to give one that is slightly larger and therefore has a cross-validation error sum of squares that's bigger, but not too much larger than the minimum possible. That gives a less complex, less flexible fit. So what we're going to do in this second part of this lecture is to compare lasso, ridge, and elastic net. A particular elastic net, I chose alpha 0.05 or sorry 0.5 for no particular reason. I could have chosen other ones, but that's the one I happened to choose on the Ames house price data.